So what else can we quantify about diffusion? So to quantify diffusion, we need to think about how much matter might move across a sort of interface. Okay, so imagine coffee going through your coffee filter. Your coffee filter, in many senses, is a plane that's been kind of bent into a cone to allow the funneling of the liquid through a point. But the point is that we have an area for that filter, and we have matter transferring across that coffee filter. So the flux of matter moving across that filter is going to be a function of how much stuff went across that filter, what the area of that filter was, and how fast it went across. So this gives us the diffusion equation with the idea of J, or flux. So flux, as we see, has to have an idea of mass moving across an area, so it's mass per area, and how long it took for that to happen. So mass per area per time is the way we calculate the flux for diffusion. Okay, so that is the easier one to sort of consider, is how many kilograms of coffee might move across a filter paper that is this in area, and how long it took for that amount of mass to move across that area of filter paper. Okay, so hopefully this piece here makes a little bit of sense to you. We realize that mass, of course, can be transformed into the number of moles of atoms or number of moles of molecules. So the format here, where we have moles of matter moving across area reflected now in, say, centimeters squared per time unit, is another format that you might see this flux equation. Okay? So how can we measure flux of diffusion? You could measure it empirically. So you could say have a thin film membrane, like we've said, a barrier, a known area, and we simply ask matter to move across it. So we impose a concentration gradient, high concentration on one side of that membrane to low concentration on the other. Again, imagine that moment just before coffee starts to move across your coffee filter paper. High concentration of coffee on one side, zero concentration on the other, and we measure how fast, in that case, water and all the molecules within water move across that coffee filter. Okay, so to help us put a bit more thought to this, J, the flux, is going to be equal to the amount of mass that moves across this membrane per area per time. Breaking out the per area piece, because that's a bit of a constant for the experiment, we now see that there will be a change in mass as a function of change in time that will help us determine the flux of material moving across the membrane of known area. So if we were to plot the mass diffused, initially there may not be very much happening until we start the clock and get things going, and then at some time later we would expect that we would start to move mass across the boundary that is our coffee filter. So we may have lots of matter here and start to move it across this filter of known area. Okay, so from here to here is where diffusion has occurred, and we started the experiment right at the beginning of this sloped area. Okay, so I think that's what we have animated here. So here you can see here that the slope of this graph is what's dictating how much we get across. So for higher slopes, more mass is diffusion across. For lower slopes, less mass is diffusing across. So J is a characteristic for how much diffuses across this material of known area. Okay. So in the case of a steady state diffusion experiment, the flux will be proportional to the concentration gradient, and that is it. So in this experiment here, we could have, say, for example, that coffee moving across the coffee filter. So here's the coffee filter into a receptacle where there is no coffee, so very low concentration. Might be one way to consider this. So the thickness of the filter is represented by x2 minus x1. And the concentration starts at a high concentration and moves down to a low concentration because there is no coffee on the other side. Okay, and so to derive sort of Fick's law here, we need a proportionality constant to help us understand the change in concentration from C1 to C2 across our boundary defined by the distance x. So x2 minus x1 is the dx of this piece. And so simply knowing the concentration difference in the thickness of our membrane, we need an additional constant out front to help us understand how much matter gets across that. So this diffusion constant D helps us equate change in concentration with thickness to that flux. Okay, so this diffusion coefficient is important, and it describes how quickly one material can diffuse through another material. So in other words, these are very specific to what is the chemical in question, what the matter is, the filter in this case, or the membrane material as we saw in the previous slide. So these have to be determined from experiment and get tabulated often. Okay, so let me just clean some of this up for us. Okay, so how does this work? Well, certain materials have a linear permeation of flux, so that is the gradient from C1 to C2 will be linear. And so if that's the case, this left-hand side of, this right-hand side of the right-hand piece of the equation is simply the delta C and the delta X, okay? So that is, if we know the concentration at the right-hand side of the boundary, and we know the higher concentration at the left-hand side of the boundary, the difference between the two is our numerator, and the denominator is the thickness of the membrane in question. Okay, so this could be as simple as knowing the concentration C1 value, knowing the concentration C2 value, and knowing the thickness of the membrane to help us with this. And if we were able to look up the proportionality diffusion coefficient, we could predict how much matter would move across this cross-sectional area per unit time. Okay, so for example, the top might be in units now, might be, say, grams per volume, and we would be dividing that by a distance in centimeters, for example. Centimeters singular, sorry, to the singular. Let me clean that up before you read it too much. There we go. Dividing through by x. So just this piece here has units that are gram per centimeter to the fourth. And we know that the flux must be in grams per area per time. So we can think about what the units of the diffusion constant should be. So the units of this should be centimeters squared to transition our denominator from to the power of 4 to the power of 2. Okay, so the units will be centimeters squared per second, because we do not have a per second as of yet in the righter portion of the right-hand side of this equation. Okay, so diffusion coefficients are typically area per time. And so that would allow us to obtain the flux in the proper mass per area per time from this equation. Okay, so maybe we'll learn that deeper or better by doing an example. So here's methylene chloride, a common ingredient for paint remover. It's an irritant, so typically when one handles this paint remover, you would wear gloves. And so these butyl rubber gloves are typically 0.04 centimeters thick. And we could provide, if we knew the diffusion constant for butyl rubber and methylene chloride, so this would be looked up or provided, we could ask an additional question. So if the butyl gloves are such and such thick, what is the diffusive flux? So we are asking what is J of methylene chloride through this glove of this thickness. Okay, so we recall J is minus D dC by dx. And if it's linear, it's going to be minus D delta C by delta X. So hopefully you're recognizing that we've been given a diffusion constant. It's in the right unit, centimeters squared per second. So we're good there. We're sort of 1 out of 3 pieces needed to calculate J at this point. We would need to know the thickness of the membrane. In this case, the membrane is the glove itself. So it looks like this thickness here is our delta X. And then we would need to know the concentration across this piece of butyl rubber. So that's where the question finishes off the detail for us. So we need to know concentration. So we might be told that the concentration in the paint remover is very high at 0.44 grams per cubic centimeter. Okay, so we're getting mass of methylene chloride per volume. And on the other side, towards your skin, it's very low. So here we have a value here that's non-zero at 0.02 grams per centimeter cubed. Okay, so our question here is to solve for the flux. And I believe through this, we now know the delta C for the numerator. So this should be a fairly straightforward calculation. We'll just make sure that units units cancel out appropriately as we do this. Okay, so J was equal to minus D. And because we're assuming a steady state linear diffusion profile, we can simply do a delta C divided by delta X. Our diffusion constant from the previous slide was 110 times 10 to the minus 8 centimeters squared per second. And the right portion of the right-hand side is a change in concentration. So we had 0.44 grams per centimeter cubed as a concentration. And then at the low concentration side of the butyl gloves towards your skin, this was a value estimated to be 0.02 grams per centimeter cubed. And the thickness of the membrane is the glove thickness. This was the 0.04 centimeters. And so we can just take a quick preview at some units here. So when we have these two combined to have the same units as presented, so grams per centimeter cubed will be the outcome of the numerator. We're going to divide through by centimeters again, so I'm expecting the outcome of all of this to give us grams per centimeter to the power 4. I recall that our units for flux should be grams per area, so centimeters squared, grams per centimeter would be good, and then per time, so dot S. Okay, so when we multiply by centimeters squared in our diffusion constant, that is going to cancel 2 of the centimeters to the power 4. So that is looking good. And then we're going to end up dividing through by the second, and that is going to give us the per second in our final answer. So that should be good. I think our units are set up, and so this should be a fairly straightforward multiply, divide type question. Okay, so after that you should get an answer that is about 1.16 times 10 to the minus 5 grams per centimeter squared per second. Okay, so that is the flux. For every second moving across an area of a centimeter squared, we would move 1.16 times 10 to the minus 5 grams of methylene chloride across these butyl rubber gloves. Okay. Kind of written up for you here in PowerPoint is the exact same solution. So if you didn't like my previous scribblings, you've got it here more formalized. So there's that same answer.